several years. And so feel free to interject and ask questions as we go along if you see anything interesting.
Okay.
Okay.
Okay, great. Thanks.
All right. Now, this was it's a 13-minute presentation that as you saw, you need to stop it.
It's stopped. It's on 314 now.
Oh, it's going all the way through, isn't it?
No, it's stopped. I put it to where you said you wanted to start it at
Oh,
314.
no. Well, go back to the very title. So I'll explain how we put this together. Yeah. Obviously, this was given a talk in Tokyo a few years ago. Demon Tong has, unfortunately for us, but perhaps for him, it's a good thing. He's retired and living happily in Sacramento, California. But he was with me for about 25 years. And he was the fellow who was responsible for many of the interesting things we've done experimentally over the years. We still do some things, and we think they're interesting. But he was, I've had the pleasure of working with several outstanding experimentalists, and he was likely the best. So we put this talk together, and it's really a combination of several projects, as you'll see in a moment. There are slides in here which I'm not going to brief today because it presupposes that you've had this course. So I'm just going to concentrate on showing you the videos and trying to explain what the videos are telling us. And then if you actually take the course, at the end of the course, you should watch this again. And I think you'll understand it better and in a deeper way than today. But this will give us a shot at what's happening initially. So if I click this, I'll get started.
It'll start playing from the beginning. Is that where you want to start?
Okay, that's fine. It only runs 13 minutes, so we'll let it run through. And this is just a list of the various wind tunnel experiments for which we have videos. And there's the math models. I'm not going to tell you the details of the math models, but there's some math models that go along with this. Oops. Okay, let me stop here. This is not the video yet, but this gives you an idea of what the physical model looks like in a wind tunnel. Over here, this is the model in the wind tunnel that's mounted on the sidewall. It's a very flexible piece of structure, so it's deflecting under gravity. The next time you're at an airport and you look at a Boeing Airbus airplane and they're on the runway before they start flying, they're deflecting under gravity. They're very flexible. Even modern commercial aircraft are much more flexible than they once were, and deliberately so. So then when you fly, the aerodynamic forces lift the wing, right? Counteract gravity. The lift has to equal the weight of the airplane, otherwise you don't get off the ground. But you'll see in the video, you'll see that wing lifting as we start the wind tunnel and the airspeed increases. Okay. And what you'll see is that when the wing becomes approximately horizontal, when the steady flow lift is bouncing the weight of the wing, that's near where it begins to become dynamic and stable. And we call that flutter. And that's the bread and butter of an aeroelasticity, right? Because most airplanes are designed to be not very far away from the flutter condition. You usually don't want to be in the flutter condition. Sometimes you find yourself in that condition unexpectedly, particularly in a flight test. Although it happened in operations, there are cases where the airplane was initially free of flutter, but they made a modification and they either didn't do the analysis or the wind tunnel testing or something appropriately, and the chief engineer decided not to do a flight test because it was going to be very expensive and delay the program. And then when they flew the plane, they discovered that was probably not a good cost-saving measure. Okay, now if you take this blue piece, this covering off, it's just a thin skin to give it an aerodynamic shape, right? If you take that skin off, this is what it looks like. It's got all these little, they're made out of plastic, actually, these little plastic rib-like things, just so I can put a cover over it, make it look aerodynamically smooth. And then this end piece it's a slender body, but slender body is actually a technical term. It's obviously a layperson term too. Slender body aerodynamics is a form of aerodynamic theory designed especially to deal with the slender body. And it's different from, say, the wing. I mean, the kind of flow you have with the wing is quite different from the flow you have with the slender body. If you take a large enough computer program, it'll deal with both. But if you use classical, I'll call it classical aerodynamic theory, which is what most people use even today in industry, at least initially. There's a code that does slender bodies, and there's a different code that does the wing, and then there's some effort to combine these in some appropriate fashion. In our case, the reason we want that slender body on the tip is that it gives mass to the wing. And by adjusting the mass distribution along the flow direction, the flow is coming in the wind tunnel, it's come from this way over there, and thankfully coming over here. By adjusting that mass distribution, we can either make it flutter within the flow speed range of our tunnel or not. If you're designing a real airplane, you add mass to prevent flutter. If you're doing a wind tunnel test and do research on flutter, you put the mass in the perfect position to create flutter. There's nothing so boring as a flutter test where the model doesn't flutter, right? That would not be a useful thing. Okay, so that's the model. Over here, this just is a cartoon. Here's the tip again. Here's the slender body. You see this metal piece, the darker piece. That's what's giving most of the stiffness to the model. These plastic ribs add a little mass, but very little stiffness.
Yeah, and it's a symmetric airfoil in this case.
Say again?
Is it a symmetric airfoil?
Well, it's a half airfoil, right? It's a half wing. It's cantilevered from the sidewall, right?
But the
Oh, you mean the
of
profile?
the ribs.
Yes, I think it's probably a 0012, which NACA 0012
So
is
it's
our favorite model. Within the framework of classical theory, and even this model through some approximation, the profile doesn't significantly influence the flutter condition. That's not true transonically. That's yet another reason why transonic flow is harder than, say, low speed flow. Low speeds, the profile shape doesn't change the flutter condition very much. So if I had a different profile, I still have the same flutter speed within reasonable limits. But if I go transonically, it'll change quite a bit because in transonic flow, I have a shock wave, and the position of that shock wave is strongly dependent on the profile. But of course, in low speed flow, I don't have a shock wave. But if I move that shock position around, I change the flutter condition a lot. And you could move the shock a lot by going from Mach number of 0.85 to 0.9, okay? And so the flutter boundary, we'll talk more about what that means technically, but the flutter boundary can be very sensitive to the Mach number in the transonic range, and the basic flutter mechanism can change. So as we'll learn in the course, there are at least a half a dozen distinct kinds of flutter. If you know, there's classical music and bluegrass and jazz and polka and whatever, right? Well, there are different kinds of flutter too. And if you're a layperson, it's all flutter, but if you're a specialist, you distinguish between those because they have different sensitivities. Different kinds of flutter are more sensitive to some parameters than others. And so that's why there are people who do this for a living and make a pretty good living on it. Did I tell you more than you wanted to know?
No, it's perfect.
That's okay.
Exactly.
All right, fine. And then, of course, we want to measure the motion, and we can observe the motion. We're going to see the video, right? But you want to measure the motion, so we put accelerometers on the apparatus. We put a strain gauge. We put the strain gauge at the root because that's where the strain and stress are highest. Ideally, you would put the accelerometer probably at the tip where the acceleration is highest, except we also have a mirror up here and we're shining a laser on it to, again, make a measure of deformation. So we use lasers and mirrors, accelerometers, strain gauges. Those are typical devices. There's some more recent optical systems, and for a few $100,000, you can buy one. And then you have to hire a technician who gets paid a certain amount of money to operate it. And so normally in a university setting, you don't have that. But if you went to an Air Force laboratory or NASA, they would have that capability. But this is perfectly adequate for most of our work. Okay. So now what we're going to see is we're going to see a video of this. Actually, we're going to see two videos. And so what will happen is at the start of the video they'll be side by side. So on the left-hand side, it's a video of what happens as we start at a low speed and increase the speed. And then on the right-hand side, it's what happens when you're at a speed beyond the start of flutter and what happens when the speed is decreased. And it turns out for this model, even though the deflections aren't terribly large, there is some hysteresis, meaning that the flow velocity at which the flutter starts when you increase flow velocity is not the same at which it stops when you're decreasing. And that's a nonlinear effect, okay? Most of what we're going to learn in the course is how to build mathematical models, linear mathematical models, but we'll touch on nonlinearity from time to time. But even at low speed, this model has a nonlinearity, and it's an aerodynamic nonlinearity. Even though the motions aren't that large, we think, based on what we've done, it's an aerodynamic nonlinearity because even for these relatively small motions, the aerodynamics at low speeds can have a nonlinear component. Okay, so I told you probably all you want to know about that, so let's go ahead. This is just some data and some comparison with computations. I'm not going to talk about that today. Maybe at the end of the course, I'll come back. Okay, so here are the two. Apparently, we have some sound. Our wind tunnel is noisy, right? On the left is we're going to start at a very low speed, essentially zero, and go up to 33.5 meters per second. Typically, we test in the range 30 to 50 meters per second, which is sort of a sweet spot in our wind tunnel. And this is a fairly typical low-speed wind tunnel. This wind tunnel normally will go up to 80 meters per second, but we've never been brave enough to run it that fast because the wind tunnel shakes, the quality of the flow goes down, all kinds of reasons not to test in that range. So our joke about our models is we discovered a universal number. All flutter models flutter at 30 meters per second because we've designed them that way. It's not, we've chosen the dimensions of the model and the materials. So everything interesting will happen in a flow range that we like. Okay. And then on the right-hand side, we're starting at a high speed and then going down. And you'll see this is one configuration. Here we're looking more end on. And because we've stopped the video, if you look at this, it's really oscillating about a point. It's moving in a pitch-like or torsional-like mode about a point, right? And you have a little blur at the ends because here the motion is very small, but at the ends it's twisting. This also bends. It bends and twists. And so classical flutter that most people know about if they don't know anything about any of the other kinds of flutter is something called bending torsion flutter. And this is a bending torsion kind of flutter. But, well, enough said, let's go. So as I turn on the video and you'll see this rise as the static, this is at a slight angle of attack, at a slight angle of relative flow, so it has some static lift on it. You'll also see it bouncing around on the left because our flow is not perfectly smooth. It has a little turbulence in the wind tunnel, so it's responding to that low level turbulence. But then when we get into flutter, you'll see the motion becomes a bit larger. Okay, so with all that, let's see what we have. Nothing's happening on the right. It's all on the left at the moment. Later you see what's happening.
I started. Technically, it's a limit cycle oscillation because of the non-nearly bounding the motion. It's not a limit cycle oscillation. Now this one is starting out with happening again. And now when I'm slow down the speed and slow speed, it's
Okay. Oh, now we're gonna see a computer simulation. So we build computer models that compare with those experiments. And so these are computer generated models. So we have a system of it starts out as a system of nonlinear partial difference equations. It gets converted through a certain methodology into a larger system of ordinary difference equations in time. And we do a time simulation. We start with some initial conditions, we let the computer run, and if it's below the flutter condition, it's an oscillation that damps out. If we're above the flutter condition, the oscillation initially grows and then reaches a limit cycle oscillation, some finite amplitude, and this goes back and forth. And we'll see how that works. So this is just two different views of the computer simulation. It's quieter, right? The wind tones up. Need to go back. I didn't realize it was quite that quick. Ah. Yes. Can I stop it? Yeah.
Mhm.
Yeah. Thank you. Well, you can say honestly, what I wanted to point out was look at how the wing is deformed. On the right, you can see it's twisting, but it's also bending. And then on the left, you can see the bending. And although this may not be something you'll fully appreciate until we get later in the course, this is a system which in principle has an infinite number of modes and an infinite number of degrees of freedom. But usually only a handful participate significantly in the flutter motion. Traditionally, for a low aspect ratio wing, that is one where the span is not too large compared to the chord, it's the first bending mode and the first twisting or torsional mode which couple predominantly to create flutter. The reason high aspect ratio wings are interesting, and by the way, they're very relevant today because the commercial companies, Airbus and Boeing particularly, want to build higher and higher aspect ratio wings because they're more efficient in terms of fuel economy, etc. Here it's the second bending or even the third bending mode that couples with the first torsion mode. And people who are accustomed to building lower aspect ratio wings say, oh, how can that possibly be? It's always the first mode. No, not necessarily. If the span is long enough, the higher bending modes couple with the lower torsion mode. And so that was a revelation at the time. At the moment, in addition to this work was done probably 10, 15 years ago. There's a group at the Technion, another group at Imperial College in London, another group at DLR, which is the German equivalent of Air Force / NASA. There are various groups that are looking at very flexible wings. Very flexible means, remember, seeing how much that bent just statically under gravity? Well, they have wings where the wingtip is bending almost half a span. under gravity. And so they're really, and that creates additional difficulties. In some sense, the fundamentals are still the same as what you see here, but this is a current topic of great interest in the research community, and there are experiments being done and also computational models being built. Okay, let's go on. Any questions? We're going to now change to a different model. Any questions about that? You're all happy for the moment? Good. So let's move right along. Again, I won't go into the math associated with these systems. Oh, let me stop here though. So we're now looking at a different model, and this is a cartoon of it. So what we're going to look at is, this is a nice rectangular plate made out of aluminum, for example. This is going to be clamped along this edge and free on all these other edges. So, and then there's an angle beta, which describes how it's rotated relative to the stream. See, the flow stream is this way, right? So if beta is 0, then this clamped edge is perpendicular to the flow stream, and sort of clamped at the leading edge. And then we're trying to get money from NASA or the Air Force or somebody, we call that a control surface. Or if beta is 9 degrees, so it's clamped along the side edge, we tell them it's a wing or possibly a fin on a missile. Okay, because generically that's what it is, right? Except it's a pretty simple structure compared to what the company might build. And so we're interested in how the behavior changes as we change beta. Also, there's an application where if beta is 0 and this is clamped at leading edge, it turns out that the amplitude of the oscillation is larger than if beta is 9 degrees and it's clamped at the side edge. And so if you want it to vibrate a lot, you want to adjust beta accordingly. And then if we're trying to sell this to the National Science Foundation, which we have done, we tell them it's an energy harvester. That is, we have created a mechanical vibration. We put a piece of electric material on it, and that converts the mechanical vibrations into electrical signal and electrical energy. Now we're talking about milliwatts. We're not talking about your local power plant, right? But if you're out in some remote location on top of a mountain, in a jungle, in the ocean, a remote river stream, you can imagine putting something like this in the flow and generating enough to power your cell phone so you can call for help. And that's one of the steps. So we've had quite a bit of work on this, not just this particular configuration. We've done 3 or 4 of these. Most recently, we had a PhD student from Pakistan. He was getting his degree in Pakistan, but he wanted to come here and use our wind tunnel. We thought that was a quite amazing. But they probably don't have a, even a low speed tunnel at his University of Pakistan. So he came and spent a year with us and doing a related experiment. Okay, sir. Let's keep going here. Oh, stop again. So here's the actual physical model. The blue is a rigid piece. It's an aerodynamically shaped piece, so the flow is smooth, going from right to left. So the flow comes over the blue piece, which doesn't move, and then it goes over this gray or silvery piece, which is a thin, flexible sheet of aluminum. And that's the part that's going to vibrate. Okay. So this is beta 0. This is the flag, flapping flag or control surface. This is, if you like, is a swept wing. Beta is 45 degrees. This is the wing or fin configuration with beta of 9 degrees. And here's an intermediate case is 71 degrees. So now we're going to see some videos showing how these move when they're past their flutter condition. Of course, the flutter speed itself, the speed at which flutter will occur, depends on beta, as well as the amplitude of the oscillation. Let's see what. Oh, this is again some detail which I won't bother you with today. But you do some static deflection tests and vibration tests that characterize the model. And this is some correlation between theory and experiment, which is not too bad. I think actually it's quite good. This is showing the amplitude versus flow velocity. And on the left and the frequency on the right.
That's so wow. Okay, here's data of 0 degrees, and it's really moving, as you can see, right? So that's great from an energy harvesting point of view. It's not great if it's a control surface on your airplane. Here it is at 45 degrees. The motion is still pretty violent, but it's not as violent as at 0. Here it is at 9 degrees. It's still pretty healthy. You probably wouldn't want to fly in that airplane, but it's not as large motion as was the case for Big Sur. Okay. This is yet a different model. The F-16, which is still probably the most used fighter aircraft within the NATO countries and other friendly powers. Australia has some. And that's the airplane that Ukraine has been trying to get for a long, long time. We finally sent them some. It is an airplane that has a wing, has a fuselage. And this is our low budget effort to mimic the F-16 in our low speed wind tunnel. Generically, it's not the F-16. Meant to be even a scaled model of the F-16. But there's something interesting about the F-16 and some other aircraft. If I have 2 wings, now we're no longer doing a half wing, we're doing a full wing, right? So this piece is our version of a fuselage. And there's a wing on this side, and there's another wing on that side, which you may have a hard time seeing in this picture, but you'll see it later on in a little more clarity. One of 2 things can happen. This is a symmetrical geometry in the sense that both wings are identical as best we can make them, right? But when this goes into flutter, it could do this. It can also do this. Okay, even though it's a symmetrical geometry, anti-symmetrical motion is perfectly possible and may be more critical. And this is public knowledge, so I'm not revealing any secret. The F-16 flutters asymmetrically, typically. And a lot of other planes do too. So there's always a debate in the community. If I'm going to build a wind tunnel model, do I build a half model, which would be cheaper and easier, or do I build a full model? And there's some folklore which is largely wrong, which I won't tell you about. But basically, there were people who thought that you show that the symmetric flutter is always more critical than anti-symmetric flutter, which is not true. What is true when you're trying to correlate, when you're trying to build a model, which you would typically test in a NASA Air Force tunnel for a real airplane, a scaled model of a real airplane, it turns out you can't get there from here in the sense that you cannot faithfully replicate all the essential features in the scale model. You can make something that look to the naive observer look like the real airplane. I mean, it just looked like a smaller version, but if you think about it dynamically, you think about all the mass, structural, aerodynamic properties that are required to be scaled, you can't really build a wind tunnel model that exactly replicates, even on a scaled basis, the real aircraft. And that's even true in low speed flow. It turns out it's even more true in transonic flow, and even more true in hypersonic flow when you have to think about the thermal field. So there's always a debate about what is the utility of the wind tunnel model. And if you have a chief engineer who doesn't understand flutter, which is perfectly possible, they may come up through some other technical path. There's a temptation for them to think that because we have a certain behavior in the wind tunnel, that's what's going to happen with the aircraft. What you're really doing with the wind tunnel model is you're assessing the quality of your computational model. And then you're hoping if the computational model works for the wind tunnel model, it will still work when you put in the appropriate parameters for the real aircraft. That's the hope. No, anyway.
So with that,
Dr. No,
Yeah.
are the inside the wind tunnels, are you able to adjust the pressure? There's like, are these tests run at atmospheric pressure?
In a low-speed tunnel, they are. In a compressible tunnel, in a transonic tunnel, what you typically do is you fix the Mach number and you change the stagnation pressure, which in turn changes the stack pressure. Am I using terms that you?
Stagnation?
Yeah, that you change the stagnation pressure, which changes the stack pressure, which changes the level of the forces acting on the model. And you go into flutter by changing the pressure that affects Mach number in a compressible tunnel. But in our tunnel, it's atmospheric pressure essentially, and we're just changing the flow velocity.
okay, let's go on here. And just some more detail on the configuration and some mathematics. We measured the natural frequencies of the model and correlate that with calculations. Here you see it a little more clearly, right? Here you see, oops, let me stop here. Here you see, it's two non-identical wings. This is the fuselage. This fuselage is free to rotate as a rigid body. It's free to roll, right? It can't move up and down. The fuselage cannot move up and down, and it can't yaw, but it can roll. So in the mathematical model, we will allow for this rigid body roll of the fuselage as well as the flexibility of the wings. Right? And we can test it with that roll degree of freedom taken out by clamping it. So then this it cannot move anti-symmetrically, can only move symmetrically, or we can let it be free to roll, in which case an anti-symmetric motion can occur. And one of the questions is which one's more critical? And you'll see the answer to that in a moment. This is just a vibration test device where we're shaking them all to see what its natural frequency look like. And this is just some test data. I won't talk about that today. Okay, so now we're going to see the ball in the wind tunnel. We have a certain flow velocity, and we'll have we remove the roll degree of freedom, so we only have symmetric flutter. It occurred at 17.2 millimeters per second, meters per second, but the antisymmetric flutter actually occurred slightly lower. Right now, that difference, well, it depends a little bit on what you're trying to do. That's not a huge difference, but if you're trying to convince the government to let you fly the airplane, and they say you must assure us within 15% that you know where the flutter speed really is. That's might be important, because if you had to make sure that it was a 17.2 rather than 6.7, you might have to make some significant change to your model that would cost you performance or weight or something that you wouldn't like to do. Anyway, we'll see what happens here. So here it is. And notice that the motion isn't purely sinusoidal. The linear models always say the motion is going to be sinusoidal in time, but real models with nonlinearities, motion may be a little more complicated in terms of its frequency content. And I think the one on the right will flutter in a moment, I hope. It did the last time. Yes. Good. Nice thing about videos, as opposed to doing live demonstrations, the videos usually work. Live demonstrations is something hard to do. Ridiculous sponsored thing. Okay, now we're going to yet a different model. And let me explain this cartoon. We're looking at a side view. This is an airfoil, right? And now we have a control surface on the back, a real control surface, right? It rotates. It pivots about a certain axis. And we're going to study this model fairly early in the course, a back model of this. And here we think of this, the airfoil itself, as having a spring which restrains motion up and down. That's called plunge. That's the jargon. It also has a torsional spring, which restrains it against rotation. We call that pitch. And then this rotation about this point
is usually called flat. These are just words, right? We could call it oranges, apples, and pears, but we prefer to call it plunge, pitch, and flat rotation. So it has 3 degrees of freedom, right? There are 3 possible motions. And we can write down 3 equations that describe those motions, and they're coupled in general. They may be coupled inertially, they may be coupled through the springs, and they're certainly going to be coupled through the earth. Okay. So we have to think about how these motions couple and may produce a form of flutter. And now this spring, we'll show you a picture in a moment. But this spring, we're going to allow it to have free play. That means the spring is not completely connected, right? It's free to move within a certain range relative to this piece before it really has any spring resistance. So you can think of it for small motion, the spring stiffness is 0. And then if the motion gets large enough, it engages and it has some nominal spring stiffness. That's what we mean. That's one example of free play. Almost every control surface built in every airplane flying has a certain amount of free play. Okay. And the design criteria, at least in the US, I think it's true in Europe and probably other countries as well, is that the free play must be small enough. And small enough tends out to be like 1/10 of a degree in terms of rotation. Can't build it that way, really. Or if you build it that way and it comes out the hangar after the first few flight tests, it's no longer 0.1 degree. So basically you can't meet the spec. You can't meet the specification by the government. So what happens is people say, well, can we have an exception to that specification? Oh, well, you can, but you now need to demonstrate by some combination of wind tunnel test, flight test, and/or analysis that if I allow you to have more free play, it's all right, meaning that you can fly the airplane, you won't have a structural failure, etc. So, and there's been a lot of discussion, but you know, your bureaucracy moves very slowly. Been a lot of discussion about changing the specification, but no one wants to do that for fear that something bad will happen and then they'll get blunt, right? You think how that might happen?
So free play is just like.
I'm sorry?
Free play just means free to rotate.
It means it's
Right.
free to rotate. It's free to rotate without any spring resistance through a small,
Without-
yes, through a small angle.
Um,
Here's a picture. This is the torque. This is the resisting torque or resisting moment as a function of rotation angle of this device. And over some small range of rotation angle, there's no torque resistance. And then you get to a large enough angle on either side, there's some nice linear behavior in terms of relationship between the moment or the torque and the rotation. So if this little piece was collapsed to 0, there would be no free play. And conversely, if this horizontal piece gets larger and larger, you have more and more free play. Of course, there's a wider and wider range of angle over which you have no torque resistance. Okay?
And
Yeah.
the free play poses a risk to the structural integrity of the airfoil.
It does. And usually it's a fatigue issue rather than a catastrophic issue. You fly this airplane a lot, it's banging away between what we call the stops, between these 2 points. And if you fly a typical commercial airplane flies with 20, 30,000 hours during its lifetime. Right? And so you go through a lot of cycles. And eventually you're going to have it's at least going to be a maintenance issue, right? You got to maintain it, you got to look for it, you got to change out the mechanical piece before it fails. And also the pilots don't like it because they can feel it. And it doesn't take much motion for the pilot to feel it. Or maybe it's large enough, the passenger might feel it, right?
This is like a motion like this, the airfoil, or just a motion
Yeah,
like this.
well, you'll see it in the video here in a moment. So let's go to the video. Okay, let's stop here. So here's the actual piece. So this is what we put in a wind tunnel. Typically, you can either test it vertically or horizontally. If I test it vertically, I don't have to think about gravity. right, which is an advantage sometimes. So here's the airfoil. This line, that's where the control surface, that's this piece, is connected to the main surface. Right? And you can't probably see it very clearly in this picture, but there's a little piece here on the control surface with a small wire, and that wire can move back and forth between two pieces which are rigid. And when it's moving between those two pieces, it's in free play. And then when it hits one of those pieces, that wire starts to bend and gives you an effective spring, right? And you can see it a little more clearly in this picture. Here's the control surface over here. We're looking at this top piece. And then here's this little thin wire, and it's going back and forth between those two pieces. I mean, this is not the only way to create free play, but this is a convenient and relatively simple one. In a real airfoil, it's not this geometry, but it's an equivalent. It's a mechanically equivalent. All right, so let's go on. Here, we correlated calculations and this is amplitude of motion and various degrees of freedom. This is the free, whoops, stop. Again, we'll talk more about that later once we've done a certain amount of discussion of mathematical model. But what you want to do is you want to correlate the motion and the frequency of the motion between theory and experiment. So remember, the motion is plunge, pitch, and then rotation, controlled surface rotation. So we're going to measure all those motions. They all have the same frequency, right? They're all vibrating at the same frequency, but they have different amplitudes and they change with flow velocity and all that. Okay, so I'm going to show you two videos. One's at a relatively lower flow velocity and one's at a higher. And see, this is looking at the end-on piece of that model. And then at some point, we'll zoom out with the camera and you'll see the whole thing moving. And what you should look for is that the motion, the various degrees of freedom are moving in different ways, depending on whether I'm at this lower speed or higher speed. What happens is that you go into flutter, you have a certain characteristic motion and a certain characteristic frequency, and then that motion itself becomes dynamic and unstable, and you go into a different motion as you go to higher velocity, and it gets bigger, which is also interesting. Okay, so let's see what it looks like. I should give you earplugs, right? To watch the video. It's not too bad. But if you're doing this several hours a day, you probably want to have earphones. So here you see that little wire bouncing back and forth. It's in and out of free play, depending on where I am in the cycle of motion. And there, that motion involves significant motion in all 3 degrees of freedom. But then when we go to the right-hand video, you'll see a different kind of motion. And that Dr. Tom and myself, some lucky student, someone within the spectrum.
Skip to the next video. Sure. Go ahead.
Sorry.
You want me to skip to this video here?
Yeah, you can.
There you go.
Okay, now if you see this one, see the control surface is moving a lot, but the airfoil per se is not. So it's a different characteristic kind of motion. And if you look very closely, perhaps you can see that the control surface motion, the control surface motion is bigger in this right-hand video than it was in the left-hand video. And then in principle, if you go to about 27 meters per second, we didn't test that high. The nonlinearity essentially becomes very weak and you get very large motions. We were concerned about destroying the model or at least damaging the model. So we never tested that high. But the reason we knew not to test that high is because we had a computational model we had some confidence in. Enough confidence told us we don't want to do that. Okay. Things. Okay, all right, now we're going to, this is again free play, but it's a more interesting model for both technical and historical reasons. Now we're gonna actually have a wing. See that previous model was an airfoil that spanned from, say, bottom to top of the wind tunnel. And basically was if you will, a two-dimensional flow, right? There was nothing happening in terms of span-wise variation. It was uniform on span-wise variation because we tested it and built it that way. Here we actually have a three-dimensional flow over something that looks sort of like a wing, but it was meant to model what is called an all-movable control surface, horizontal or vertical, usually horizontal. So now it's going to be pivoting and bending about this axis, and the free play is in that root connection in the pitch degree of freedom. But now this model also bends or twists all along its span, right? So it's a more complex model. This happens to be the model that the Air Force tested some years ago. Not the exact model, but it's more or less a modern reincarnation of it, which led to the design criteria, which I talked about. At that time, very little was known about nonlinear dynamics. This is decades ago. And so they interpreted their data incorrectly. I won't go into all the detail. But that led to the design criteria we currently have, which is still persisting. So this was an effort to redo the test, interpret it in modern nonlinear dynamics understanding, and convince the government that they should change their design criteria. It hasn't happened yet. And it won't happen just because Duke University says we should do it. It'll happen because the community, particularly the aerospace companies, won't be able to convince the government. They haven't done it. They haven't convinced the government yet either. Okay. Well, let's go ahead. This is some detail. I won't tell you about that. Again, we took some data. I won't tell you about that, not today at least. Okay, so now we're cantilevering this wing or all movable control surface from the ceiling, right? This is the ceiling of our wind tunnel, and again, initially to avoid the effects of gravity, but later on we tested it horizontally as well, which makes it more interesting but also more complicated. So let's look at this. We're looking down more or less on the top, sort of at an angle. And this is a grid that allows us to see roughly how large the motion is. And then the side view should start oscillating here in the middle. If all goes well. There you go. These are not huge motions, but they're enough to be structurally significant and also significant to the pilot if they're trying to control the airplane. Okay, let's keep going here. What did I do wrong?
Check the ending.
Go ahead.
It's buffering. Reloading. We were about. So this
Keep going,
here.
keep going. Keep going.
It's just the next slide after those videos.
Okay. No, I was trying to zip by, yeah, yeah, that's fine. I think it'll get into where I want.
Okay.
We tested with and without gravity and took some data, but here's why I wanted to show you. Now we're testing horizontally. Gravity is there. And if you look at the motion on the left and then on the right, you'll see it's not sinusoidal in time. It's chaotic. And that's another indication that this is a nonlinear dynamical system. And if you look at the time history, it would look like a random vibration. It is a random vibration. Theta naught, you see that variable. Theta naught is the initial angle that the root takes place. So we can set that angle, and you get different behavior depending on where you set that angle. Okay. We've got one more. Well, I'll let them. Well, we've got one more model. I'll show you. See this. There she's up. Okay. This is actually a buffeting area. Okay, so let's stop here for just a moment. Aeroelasticity formally deals with the dynamical interaction between a flexible elastic structure and the aerodynamic forces, hence aeroelasticity. The flow itself can be unstable, even if the structure does not move. Okay. The classic case is a laminar flow becomes turbulent. That's a dynamic, it's a dynamic instability of the laminar flow leading to a fluid only oscillation. But even if the flow is turbulent, under certain conditions, turbulence, which tends to be a small scale in space, and amplitude oscillation, can become much larger scale in space on the order of, say, the boundary layer thickness is small compared to, say, the core of the airfoil. But there can be buffet, which is an oscillation where the appropriate scale is actually the core of the airfoil. The oscillation can be rather large. The lift coefficient, if you know what a lift coefficient is, can be of a significant fraction of 1, which is a huge lift coefficient, oscillating lift coefficient. And an airplane that's suffering buffet is in bad trouble, in the pilot in bad trouble. So, and it's a phenomenon which is still not well understood. And if you ask a typical aerospace engineer who works in dynamics, what the biggest thing you don't really understand very well, and that more often than not, they'll say buffet. Yes.
Is buffeting and like fluttering the same? Or-
No, it's not really, because in flutter, it requires, at least the usual definition of flutter is a dynamic interaction between the elastic deformation of the structure and the flow field. And if you don't have the elastic deformation, then flutter per se doesn't occur. But in buffet, the flow itself can be dynamically unstable.
Oh, even if the airfoil is.
Even the airfoil is not moving.
Okay.
And so at low speeds, you have to put the airfoil at a very high angle of attack to see buffet. And it's somewhat broadly related to stall. Have you heard about that? So if I take a 0012 NACA 0012 airfoil and I crank up the angle of attack, the mean angle of attack, airfoil is not moving other than I'm just changing the angle of attack from the flow pattern. Up to about 10 degrees, the flow is smooth. It's not oscillating, it's really in time. But when I get somewhere between 10 and 15 degrees angle of attack, the flow begins to oscillate. It actually looks chaotic at those angles. But then if I put it up to 30 and larger angle of attack, I see a very strong single frequency oscillation of the flow. If I took that airfoil and put it very large angle attack, it becomes a bluff body. And how many people know about a von Karman vortex screen? You know about it's a bluff body. It becomes like a von Karman vortex screen with a characteristic frequency. Von Karman said that in his entire career, which is quite illustrious, he had 2.5 really good ideas. One of them was the von Karman vortex screen. By the way, he said Einstein had 4 good ideas. So he, on a scale of Einstein, he was 2.5. Einstein was 4. On that scale, most people probably don't have even more. Right? So anyway, so this was a big deal when it happened. People just years ago, but now we know in modern aircraft, you can get buffet. Well, here we go. This is essentially doing the calculation. You at a Mach number of 0.75 or something, you can get buffet in the range of 3 or 4 degrees. And so if you have a high-speed maneuvering airplane, which wants to be in that angle of attack range, it's very easy to go into a buffet condition, and that's not a good day. So a lot of people are going to buffet. So in our low-speed wind tunnel, we cannot get buffet at 3 or 4 degrees, right? We have to crank it up. So I think these tests I'm going to show we're probably at about 40 degrees, which is not where you want to fly a real airplane, but if you want to steady buffet in a low-speed wind tunnel, you can do it, but you have to accept that that's the condition you're testing. So anyway, this is a model where we have pressure, this is a profile. We have pressure transducers at all these points. So we're measuring the fluctuating pressure on this airfoil. And this is just, here's the airfoil, and we're just opening it up so you can see all the wiring there, all the tubing required to get to the pressure transducer. And here's the airfoil in our wind tunnel, again, going from ceiling to floor, but it's at a high angle of attack. I don't know what that is, but probably like 30 or 40 degrees. Okay. So, but we're not going to, initially, we're not going to see the airfoil moving because it's not intended to move. But then, just so you can see something, you can take a little piece of the trailing edge of the airfoil and make it a flap or a control surface. You can put free play in it, and then you can see that move. But see it move, but now it's not really fluttering. It's really the oscillation of the flow because I'm a high angle of attack and the flow is unstable, and that oscillating force is driving that flap with a free play spring. So that's what you're going to see. Okay, so let's go ahead and do that. Oh, this shows the buffer frequency as a function of flow velocity. It's a straight line because it's a well-known scaling that scales that way. We can also, however, having said that, we can oscillate this model, but we oscillate it through a prescribed angle. We control the amplitude, the angle, we control the frequency. And there's another phenomenon known as lock-in, where if you choose to prescribe an angle of that motion, which is near the characteristic buffer frequency of the naturally oscillating flow, you can move the frequency of the oscillating flow to be equal to your prescribed angle. But then, yeah, here's that little control surface. Then the other thing that can happen is if the natural buffer frequency, this is the frequency of the flow, even when the airfoil is not moving, if that happens to be close to the natural frequency of now elastic structure, those two frequencies are close to each other, you get now a significant fluid structure interaction. In some sense, that really is the airlines. And you want to avoid that. And that occurs in airplanes, it occurs in smokestacks, it occurs in submarine periscopes, any large object that looks like a bluff body and the flow goes past it, and the object is flexible enough, even the smokestack in a high wind. A tall building presents a bluff cross section, and they have this fundamental thing. So civil engineers study this sort of thing. Okay. I think that's really it. Uh. Stop the video. Okay. So. Any further questions? About any of that? No, you're happy? Okay, so I thought that would be good to get you in the spirit of things, as it were. So Flutter's a real thing. When we go through the course, we'll be building some mathematical logic and saying, well, what does that have to do with real thing? Well, it has to do with being able to try to predict or correlate with that kind of experimental data. If you're a person in the industry, you're trying to make sure your computational model is adequate to prevent anything bad happening. Or if it does happen, in some cases, there are some cases, F-16 is another example. There are some cases where flutter occurs even though you didn't want it to. But if the amplitude, because you're going to a limit cycle due to a nonlinearity, if the amplitude is small enough, you are faced with, do I fix it and prevent it altogether, or do I live with it? And it depends on how big the oscillation is, right? It also depends on the type of vehicle. There's some launch vehicles that have flutter problems and they choose to live with it, okay? Particularly if they don't plan to bring the launch vehicle back. If you fire a missile, and you're not thinking it's gonna come back, you hope it's gonna hit somebody else and never come back, then you might choose to live with flutter, provided it didn't compromise the performance of the missile. The Saturn launch vehicle, a moonshot thing, had a flutter problem, but it was small enough amplitude, they decided to live with it rather than spend the time, effort, and money to prevent it. So, okay. Now, we have we have all 5 minutes left. Let me remind you that you are to read up to page 25 in the book, right? And let's see. I've only bought 3 books. So
I have one.
you have one. Ah, now you have one. Harry, you don't have one, do you? You have one now. Now I'm gonna give one to Julie. Nick will get you one. Oh, I know what. You've got an old version, right? Give your old version to Nick. You can
Okay.
replace it with this.
I'm not like enrolled in this course.
Huh?
I'm not enrolled. in
Oh,
this
you're not
course.
officially enrolled.
No, I got your email yesterday.
Okay.
So I stopped by.
Okay, all right, fine. Well, then you
But
can,
now I'm
you can have
interested.
that. You can
Yeah,
give
that's
that.
okay.
Nick is not officially enrolled either, but you're gonna attend most of the classes we
I'm
sent.
thinking about auditing it, so.
Okay, all right. I'll let you two share it back. and forth. Actually, we may have, I need to get Louisa a copy too. Does Lisa have one? I don't think she does. I'll get, I think we have 1 or 2 more. These are tremendously expensive.
Yeah, it looks
So,
expensive.
what this obligates you to do is I get 10% of your salary for the rest of your life.
You're gonna have to
If
give
you,
it
if
over.
you accept it. No,
Just,
no, that's all right. That's all right.
What's the course?
775.
775.
It's the very bottom of the list.
So for those of you who are planning on being here on Thursday, read up to page 25. And we're gonna start out studying static elasticity. All these films are basically about dynamics. But we're ready, not, at least I don't think we're ready to do that yet. So there are some interesting static issues where there's an interaction between the flow and the structure so that the final static configuration is different because of that interaction than it would otherwise be. And that's basically what chapter 2 is all about. So we'll do that. We're gonna have homework, right? We need to have homework. So when I sent an email to you, or maybe it's through Canvas, not only did you have a link to these videos, which you're welcome to watch again at any time, there was a copy of a paper, a journal article that discusses the work behind this set of videos and so forth. So your first homework assignment, we'll make that due a week from Thursday, is to read that paper. They're gonna have a lot of things to read. And I want you to write down the 5 most interesting and or singular things you found in that paper. And then I'm going to ask you to do that again at the end of the course. And see if your answer changed. We hope it will, because by the end of the course, you should read that paper and look at these videos with a greater understanding and appreciation than you can today. In some sense, the goal of the course is so you can read the literature in this field with some greater appreciation and understanding than you can at the moment. So to do that. Yeah, so the next class, I'll start talking about chapter 2. And I'll talk about the 2 static aeroelastic phenomena of interest. One is called divergence, which is the static counterpart of flutter, which is the dynamic counterpart of divergence. And then we'll also talk about control surface reversal. And I'll just say a word about that and then we'll stop for the day. If I have a control surface, I rotate the control surface to get greater lift on takeoff and landing, right? But if that surface is connected or itself is elastic, if it has elastic deformation, the deformation can be so large that you don't get any lift. Or even worse, or at least more interesting, the lift is negative rather than positive. I rotate the control surface down thinking I'll get a greater lift up, and I get greater lift down because when I rotate the control surface, because this is springy, the wing is springy, the spring, it actually creates a moment and I twist the wing down and I end up with less lift because I rotate. That's not an instability. It's not disastrous, except in that if I need to control the airplane because that's why I have the control surface, that may be disconcerting, right? So we'll talk about divergence and control surface reversal. We'll build math models that describe how that works. And that's what chapter 2 is basically all about. And we start with simpler geometries and simpler models, and we progressively go to more complex ones that might actually be used by someone working at Boeing, Airbus, or whatever. So start reading chapter 2. Any questions before we?
I have a general question.
Yeah.
So these experiments that you showed, they were conducted between like 10 and 40 meters per second. When that's scaled up, about what speed is that?
Oh, it could be anything, depending on how you build it. But since we say, so you, well, I'll say this. Fundamentally, it would be, if I really wanted to build a scale model in my wind tunnel of some real airplane, which one could do. I mean, people do wind tunnel tests for real airplanes in a low speed tunnel. You're talking about something that's subsonic, right? Because when you get into the transonic, supersonic range, you have shock waves and all that, and it's just not reasonable. So you could go up to Mach 0.7, maybe even 0.8. So if the speed of sound is 343 and you're at 0.8, I can put the down. You might get up to 300 meters per second. If my real airplane flew at 300 meters per second, it would not be totally irrational to build a scale model and test it in a wind tunnel where the flutter speed is 30 meters per second, but I could rationally see if that is really what the real airplane would do at 300 meters per second. But if I get above Mach number 0.7 and 0.8, probably I need to really be in a transonic tunnel to get meaningful data for a real airplane.
Okay.
Yeah.
So is this concerned with like commercial airplanes or more so government?
For a low speed wind tunnel, Boeing will do flutter tests, and I assume Airbus does too, in a low speed wind tunnel. Typically, if they're going to do a wind tunnel test program, they will do some low speed wind tunnel flutter models to get a sense of what happens. But then if they're still concerned, it's really about margin. If I, either from computation or a low speed wind tunnel, I think that the flutter speed is going to be 300 meters per second. And I plan to fly my airplane beyond that, then I'm going to take my model and, or a different model, but equivalent model to NASA Langley, where they have a transonic dynamics tunnel, which is the standard tunnel in the United States for commercial based flutter testing. And there are comparable models in Europe and I'm sure in Asia as well. So does that help? Yeah, okay. It's all about margin. If I have a computational model that I have pretty good confidence in, and my computational model is predicting that the flutter speed is twice where I plan to fly my airplane at any Mach number range, I think good enough. I mean, my computational model is not good, but my computational model says I have a 25% flutter margin. I probably don't want to rely on just on the computational model. I want to do some wind tunnel testing. And every airplane that I know of any significance, they do a flight flutter test. Even if they have chosen not to do a wind tunnel flutter test. And sometimes they choose not to do that because they think, based on experience and their computational model, that they have enough margin. The government will not allow them to fly the airplane in service without doing a flight flutter test. So it may be very boring, right? They be doing lots of flight flutter tests and they don't get any flutter. Well, that's good if you're building a real airplane. Not good if you're doing research, but it's good if you're building a real airplane. So, it's computational models. It may or may not be a wind tunnel model, depending on how much margin your computational model gives you. Well, it certainly will be a flight flutter test, even if you think that airplane is really adequate based on experience in your computation. The other thing I should say about the F-16, I keep bringing up the F-16. F-16 is wonderful because it had a lot of flight problems. But the reason it had a lot of flight problems is the basic airplane, its flutter speed is way beyond where anyone plans to fly that airplane. But they start hanging stores on it, otherwise known as fuel tanks, missiles, bombs, and that all changes the dynamics of the structure. It changes the aerodynamics of the flow. And so, and there are a whole host of store combinations the Air Force needs to test. And they have chosen largely not to do wind tunnel testing. They do run computational models. The computational models are used to select the most critical store combinations for flutter. And then they go out and flight test those. But they can only do 20 combinations per year in their flight test program. And typically there are hundreds, if not thousands of combinations that the Air Force is interested in. Okay. And it's a big issue because the F-16 is an old airplane, but although it keeps getting improved. But the thing that really changes it from an aeroelastic point of view is they keep finding new missiles and new smart bombs and other things, new fuel tanks to hang on to it. And so it becomes a new airplane from an aeroelastic point of view every time they change the store combination. And they need to clear that airplane. Clear meaning they need to convince themselves that it won't have a flutter issue. So it's a flutter issue. So creates lots of jobs in airline stations. The F-35, the F-22, well, the F-22 only has internal stores, which means it's not, from an aeroelastic point of view, not a very interesting airplane.
It has fuel tanks for the wings though, on occasion, so they had to do that.
Yeah, and the F-35, I think can have external stores, but usually doesn't, I think, in its.
Not for its stealthy configuration, but it can have stores also the same place the F-16 does.
Yeah, but you had to start adding stores to an airplane, which might be very benign from a flutter point of view. It might suddenly become flutter critical. And then if there are many different kinds of combinations of stores, that generates a lot of work for somebody. Okay, we'll see you on Thursday.